Welcome to Lecture 5. Today we're going to talk about derechos, which are really an amazing, fascinating type of weather. Um, this goes back for me to February 16th, 2001, when a derecho went through here in Starkville, right through our campus. We had 110, well, the wind gauge failed at 110 miles an hour on North Farm. And at the time, that was by far the fastest winds I've ever seen in my life. Um, a lot of times people think 100, 110, that doesn't sound that bad because you hear about hurricanes with even faster winds or tornadoes. But 100-mile-an-hour winds is no joke. That is some fast winds. Really, it's almost impossible to stand once you get to that level. And even at 89 miles per hour, it's really hard to stand. People don't really fully understand how fast that really is. I see a lot of times with thunderstorms, the winds are blowing maybe 40 miles an hour, and people are like, oh, what is that, 70, 80? No, that's more like 35 or 40. So 100 mile an hour plus is a big, big deal. And this was a pretty eventful time in my life. The derecho happened February 16, 2001. On February 18th, Dale Earnhardt died. I was a big fan of his. So you kind of had those back to back. And then 6 days after that, I started chasing. I went on storm chases before in high school, and I got in my car and thought I was chasing. But February 24th was the first legitimate, what I really consider my first real storm chase. This also led to our symposium here in Mississippi State. Because of this event, it got everyone really, to come together and go, you know what, we should start a symposium down here at Mississippi State. And we did. And the next year was the first year of our severe storm symposium, which we still have today. And I highly recommend, if anyone's interested, to come see campus and come to a great symposium where we have great talks from the broadcast world and the operational side. And we've had speakers from, Greg Forbes to people from the SPC, the Hurricane Center, great broadcast meteorologists all across the country. So this event kind of springboarded all that. So again, I really like derechos. It's something fascinating, and really it was something that kind of gave me that little extra push to take my forecasting and storm chasing and meteorology to the next level. All right, so here's a pretty cool derecho. You see how it's kind of, they called this one the right turn derecho. They have names for different ones. There's one that went through Memphis many years ago that they called the Hurricane Elvis. So they got different names for these. But obviously you can see that turn to the right. Well, one of the reasons why it turned to the right is this is where all the instability was, so it's moving towards that instability. So these derechos are cool. They can do all sorts of crazy movements. Sometimes they're really simple. Sometimes they're more complex. So derechos are really cool. And, it's interesting. Like, if someone's home's destroyed by 100-mile-an-hour winds, it's almost like people get upset when you tell them it's straight-line winds versus a tornado. 100 mile an hour is 100 mile an hour, whether it's twisting or is going in all one direction. It's still big problems and can cause extreme damage. But for whatever reason, people seem to get upset when you tell them it's straight line winds versus tornadoes. But what they need to realize is derechos are, I don't want to say cool, but are just as amazing and complex in many ways as tornadoes. So just keep that in mind. If 100 mile an hour straight line winds are coming, probably going to cause a lot of damage, and it doesn't have to be a tornado. If it's all moving in one direction, it still can cause big problems. So what is a derecho? It's defined as a widespread and long-lived windstorm associated with a band of rapidly moving showers and thunderstorms. Usually what? A squall line, right? It's the Spanish word for direct or straight ahead. And it was first used by Dr. I think it's Heinrich as a way to distinguish between tornadoes and straight line winds. So, for the longest time, people thought, well, it's just tornado. Well, if all the wind's moving in one direction, that's straight line winds. It has to be twisting for a tornado. All right, so some of the classification here. It produces straight line winds or gusts greater than 50 knots. So what is that? Severe storm status there. Over an area with a major axis of at least 250 miles. So this is not some small little area. This is at least 250 miles of 50 knots plus winds. Within those 250 miles, there must be at least 3 reports of EF1 damage and or gusts 65 knots or greater separated by 40 miles. So within the 250 miles, you have to have at least 3 reports of EF1 damage or 65 knots or higher, and it has to be separated by at least 40 miles. This is showing that it's continuous. It's not just for 50 miles or 100 miles. It's at least 250 miles. And no more than 3 hours can elapse between wind gusts or damage reports. All right, so again, continuous. Derechos evolve eventually from squall lines. All right, so that should make sense. And squall lines are just linear groups of thunderstorms in various stages of evolution, from the cumulus, the mature, to the dissipating. All right, depends on the strength and other factors involved in how they're moving. They can also be composed of supercells. You can have a squall line with supercells embedded in the line that can produce tornadoes that are completely rain-wrapped. And you could argue in many ways those are more dangerous because you can't even see what's coming. The thunderstorms in the squall line, generate something called a cold pull. And we'll talk about that in more detail. You got the rear inflow jet coming through the back, which is causing evaporation, which is causing precipitation to move towards the surface, and that forms a cold pull. And you got to have a balance between the inflow and the outflow, and then everything come together in the supercell dynamics for them to stay in balance. Because if it's out of balance or out of whack, it's either going to weaken quickly, or I guess if it was the other way, it could strengthen really fast too. All right, so this is kind of what I was just talking about. The cold pull develops as a result of precipitation drag and evaporation cooling the mid-levels. It has a higher relative pressure and density than the surrounding areas. So obviously where this cold pull is, it's more dense. So it'll kind of like, I want to say a bulldozer because that's oversimplification, and that's going back to intro to met, which is really not a technical way of saying it. But that cold, dense air is moving out in front, right? It's kind of displacing the air out ahead of it. Once it strikes the ground, it spreads outward. It moves forward with the low-level winds. So you got to have this good combination, right? You got to have that warm, moist inflow with that, you got the drag here, and then you got the rear inflow jet that's forming. And there's lots of other things going on here with the supercell dynamics. It can go back to looking at things like the Lemon-Doswell model with the divided mesocyclone, Klemp. So there's different ways of looking at this. But the bottom line is you got to keep it balanced. You got to have the cold pull, but you also got to have that warm, moist air at the same time. The more it stays in balance, the stronger they will continue to stay for a longer period of time. Once it gets out of whack, things start to go haywire, and they either weaken. Usually it's what happens is it weakens. The cold pull cuts it off, and then the storms really dissipate quickly. So the cold pull with shear and LFC, you want a balance between the ambient shear and the cold pull as well as the height of the LFC. This contributes to the duration of the squall line derecho. The more in balance it is, the more they are working together, the longer the squall line and the derecho can last. The squall line will propagate for a longer period of time if the shear and cold pull are in balance, and the LFCs are low enough for parcels to rise on their own after being forced to rise. So that goes back to that 0 to 1, 0 to 3 as well. You don't want really high LCLs or LFCs because that's not really going to be able to help sustain the storm. You want them a little bit lower. Bow echoes is just a radar signature most commonly associated with the derecho. A lot of people call it a bow echo, and it's indicated by a bulge in the squall line. Most people have seen this, I would hope. The bulge indicates the presence of faster moving winds produced by the descent of the rear inflow jet. We talked about that. There's obviously much more involved in this. It gets very complex in some ways. I'm sure in your severe weather class now that most of you should be in, you're learning a lot about this, about the supercell structure. But again, this rear inflow jet forms. It kind of evaporates and erodes through the back of it, which you can see on radar signatures, which I'll show you. Then you got the cold pull. If it stays in balance, everything's going to move in an efficient way. The rear inflow jet is produced by pressure differences within the squall line between the cold pull and the ambient warmth. Well, what is the ambient warmth? Well, in the mid-levels, what's happening? Latent heat release, right? So you got some warming there, right? What's one of the best examples of latent heat release? A hurricane, okay? So the apex of the bow is the region where the most significant wind damage typically occurs. So let's kind of break this down, right? You got your bow echo here. You got a mixture of storms, but where's the worst going to be? It's going to be where it's bowing out, right? You see this rear inflow jet cutting through the precipitation. You can see that as evaporation is occurring, it's eroding what? Those higher precipitation rates. And you can kind of see where that rear inflow jet's setting up. Where that's setting up and how fast and how imbalanced everything is will dictate how far this will bow out. The more bowed out it is, typically the stronger the winds, because the tighter the gradient here, the faster the winds are going to be, all right? Just like the tighter the gradient with a low pressure, the stronger the low, the tighter the gradient here, the faster the winds, okay? So that's something to keep in mind. So here's your apex of the bow. Here's your rear inflow jet, which forms something called a rear inflow notch. You can kind of see that notch. It usually lines up with the apex of the bow, whereas your strongest straight line winds will occur. Your worst damage will be right here along this area here. And that doesn't mean you can't have bad damage here or bad damage here, but just in general, the fastest winds and the worst damage will be in this area here. All right, so there you go, rear inflow knots, which is helping form the apex of the bow. All right, so bow echoes. The appearance of a bow echo often leads to something called bookend vortices, all right? I'll show you an example of that here pretty soon. These circulations, which is usually cyclonic to the north and acyclonic to the south, form, it's very similar to the double vortex supercell model. And hopefully in severe weather, you guys will go through this in more detail. In this case, the horizontal rotation is forced downward. It's best if I just show it to you, right? All right, so you get your lines start to form. That rear inflow jet starts to strengthen as the cold pull and the warmth of loft of the latent heat release start to counteract with each other. You start to get circulations within the supercell. Rear inflow jet forms. You're starting to get that notch right here. Here's the apex. Here's some of your fastest winds. It continues. But what will happen is you'll get two circulations if this really becomes mature. On the north side here, you got your cyclonic circulation. On your south side, you have your anticyclonic circulation. So, yes, your fastest winds, and sometimes you get some weaker tornadoes here on the apex, but you can also get tornadoes on the cyclonic side, and you can get anticyclonic tornadoes on the southern side. One of my mentors, his name is Jim Leonard, who unfortunately has passed away, was the first person to ever videotape an anticyclonic tornado, all right? And it's out on the plains. He was out on, I believe it was sometime in the 70s. He started chasing the early 70s. So I was blessed to learn a lot from him. But he was the first one to actually get this on video. So it was really cool. I think his video is still out on YouTube. His name is Jim Leonard. So check that out. His website is cyclonejim.com. All right. So he's probably, before he passed away, he's probably in like 70, 80 hurricanes and typhoons. I mean, he was the pioneer of hurricane chasing. He was the very first person to ever chase a hurricane that we know of, at least. And, he's in the 80s flying out to the Caribbean chasing these storms. In the early 90s, he would go out to Guam and places like that and go after typhoons. So he was an amazing guy, great man. I learned a ton from him. And what's ironic, he never took a meteorology class. You know what his class was? Going out and actually being in it. So just goes to show there are people out there that may not have meteorology degrees that are really, really smart when it comes to meteorology. Farmers, for example, if that's your living and your dependency depends on all that, you're probably going to be a pretty decent meteorologist, right? You may not have the title and the degree, but you're still a meteorologist, at least in my eyes. All right, so derecho again, downward descent of the rear inflow jet leads to strong winds at the surface. These winds will evolve into a derecho as long as the proper conditions exist. Again, you have to keep that balance. Now that we know where they come from, let's kind of break down the environments that produce these various types. All right, so here's a great image of it, just kind of showing you how complex it is, and they try to even simplify this. You got your motion, you got your descending rear inflow. This will kind of erode this out, kind of forming that rear inflow notch. And then as this moves out, you get some bowing out there. So obviously this is, a great visual example of it, but it just shows you there's a lot going on with this. So there's different types of derechos. The most common is serial and progressive. You do hear of hybrid. Low dew point, that's a fairly recent one. When I was first learning this 20 years ago, I never even really heard of the low dew point one. But really focus on serial and progressive. Those are the main ones that you really need to understand, because those are typically the ones you're going to experience. Whether you're in the northern plains or down in the south, you get them all over the place. You've had them in Washington, D.C. You've had them, like I said, in Memphis. You had them all over the place. You can get derechos all over the country. All right, so a serial derecho is produced by multiple bow echoes embedded within a squall line. When you have these multiple bow echoes, it kind of looks like a snake or like an S shape. Those are called line echo wave patterns, all right? LEWP. They're usually several hundred miles in length. They tend to occur between September and April, and they have more of a north-south orientation, all right? So some of the features with a serial derecho, you have strong upstream trough, warm sector of the strong mid-latitude cyclone, left exit region of the jet streak. Low-level jet will supply instability and low-level momentum. So again, you have to have that balance. Yes, you have the cold pull, but you also have to have that warm instability being sucked into it as well. Soundings tend to be cool and dry overall. This is typically, you see these serial derechos associated with a high shear and low cape environment. Remember when I told you about the beginning, the derecho we had here, that was a more serial derecho, even though it had some of the progressive kind of feel to it, which we'll talk about here soon. And again, you can get hybrids, so you can get a mix of them. But that was more in the cool season where it was much more shear driven versus instability driven. All right, so the serial is associated with high shear and low cape, common to cool season severe events. May also occur with dry lines and outflow boundaries. So it's not always just as simple as just a little squall line. Sometimes it can be much more of a dynamic, bigger scale type thing as well. I mean, you can still get dry lines pushing through in February. One of the best examples of a big severe weather outbreak in February was the Super Tuesday outbreak, right? So it does happen. So you see it kind of looks more like a snake. It's got those S shapes. So you kind of see the rear inflow jet here. Like, now, obviously, you can have severe weather all along this, right? But let's just break down this. This right here is probably your fastest winds, where your tightest gradient is. Your rear inflow jet is trying to form a notch. It's not super defined here, but you try to see where it's eating away. Fastest winds here. You can definitely get, I don't necessarily want to call it spin-ups, but just weaker, less dangerous tornadoes. But even though if it hits your house or your mobile home, it's still a big problem. But still, you get these weaker tornadoes on the apex. You get cyclonic here. You would get more anticyclonic here, just if I just cut this part up. So you can see it's more of an S, more north and south shape. Progressive, characterized by a single bow-shaped system, which propagates north of a parallel east to west boundaries, kind of more of a stationary type situation. These tend to occur more in the May through August range. And again, these are more west to east, singular bow echo. So a couple things with this: downstream of a ridge, near the right exit region of a jet streak, east-west stationary boundary usually provides convergence and uplift. Low-level jet supplies instability and low-level momentum, so nothing changes there. Even though they're two different types of derechos, they're still kind of coming together the same way, all right? And the soundings are warm and moist, so this is more of a low shear, high cape, so it's opposite of serial. And these are, these actually compose the majority of derecho events. But again, like I said, you can get a hybrid where it's a mix of them as well. All right, so here's derecho. This one went through Washington, D.C. It actually caused a lot of power outages, millions without power. You're getting gusts in that 80 to 100 mile an hour range. And I know that doesn't sound like a lot, but it actually is, all right? And even in an urban environment, what do you have? You have all these buildings. So 80 mile an hour winds being pushed through all these buildings is going to accelerate, right? So that's another thing to consider. So this was just I don't want to say famous, but fairly well-known derecho event that caused a decent amount of damage all through, like I said, Washington, D.C. here. You have all sorts of them. If you Google derechos and derecho events, you'll see all sorts of different famous events. Hybrid, we kind of talked about that. It's kind of a combination of both. These may exhibit more of a zonal or a combination of trough and ridge. So you kind of, again, like in weather, are you always going to get one or the other? No, you get a mix of both all the time, right? So a hybrid would be a mix of that. And they have no particular season or distribution. I say this all the time in winter weather. A snowflake doesn't have a GPS or a calendar. It doesn't know the time of year. It doesn't know where it is. It's just going to react to the environment it's in. Same thing with severe weather. Doesn't matter whether it's May or December. If the ingredients are in place, they're in place, and you'll get severe weather. Low dew point. Again, this is fairly recent, but this looks like it's more of a dry type situation, obviously with low dew point. But it's a variant of the hybrid. But these form really in more dry environments, all right? So this would be more of a dry microburst versus wet microburst. Wet microburst more the common serial and progressive derechos, dry microbursts, these low dew point events. Not overly familiar with these because, again, I don't really live in that part of the country, and this is a fairly new term that I've only seen in the last, I don't know, who knows how long this exists, but I'm only seen it in the last 10 years or so. All right. So supercells versus derecho. Chuck Doswell, who is one of the more famous researchers when it comes to severe weather, found that in environments which support strongly forced derechos, cold season cereal, is quite similar to the supercell environment. He studies all sorts of things, but he studied in this event that the EHI can be used as a way to kind of discriminate between the two, all right, using both SRH and CAPE, which is how you get EHI. SRH times CAPE divided by 160,000. Now, you got to be careful. Just because you have a high EHI doesn't necessarily mean you're always going to get big tornadoes, because it could all be CAPE driven or all be shear driven. What you want is that balance, all right? And it's kind of going into the same thing here. He's just basically showing you as the EHI goes up, in general, that tornado threat goes up, which makes sense. But even here, you got to be careful. Even if you have an EHI of 5, if it's all CAPE driven or it's all shear driven, you're probably not going to get big tornadoes. But he's just showing you that these strongly forced derechos kind of in between here. You got your non-tornadic, and then you got, keep in mind with these derechos, you do get, weaker tornadoes within it, all right? So this is some of his research on this. He has all sorts of awesome research. If you Google Chuck Doswell, he has books, he has tons of papers. So if you're interested in more in this low-level thermodynamics, which is kind of what I did a lot of my thesis on and I really like, definitely Google his name. All right, so evolution between an HP supercell to a bow echo. You get your supercell forming, kind of hooking here, and then eventually, usually as occlusion takes place, now you kind of set up that rear inflow jet, that notch starts to form, and then it can evolve. You can start with like one cell or a couple cells, and that can quickly evolve into a bow echo, all right? So here's the evolution of HP supercell to a bow echo. The arrows show the rear downdraft, and again, you got your forward flank, you got your rear flank. If you don't really truly understand the whole dynamics of the supercells, definitely look some of this up, but also hopefully in your severe weather class right now, you're learning a lot of that. All right, so key considerations for derechos: instability. CAPE develops and maintains the thunderstorm, so you got to have that balance with the shear, enough to keep the cold pulls and thunderstorms together with the speed and the forward motion and perpendicular. If it's not in balance, it's probably going to collapse. It's probably not going to be able to, continue going, right? Now, initially, if it's more in balance to strengthen, okay, it will strengthen. But even then, you could have all the instability in the world. If you don't have the cold pull balancing it out, it's still also going to collapse eventually as well. Boundaries, acid convergence for thunderstorms, not just with derechos, but with tornadoes, with everything. Boundaries are key, and they're tricky, but you can still see them a lot of times on satellite and radar. And when you see these boundaries set up, that's usually a good spot to look for not necessarily severe weather, but even enhanced even more than what it already was. You got your mid-level dry air, which is important. That's how you get your rear inflow jet and your notch there. It evaporates, causing the cold pull, and it helps drive the mid-level winds to the surface. All right, that's how you get that fast flow to the surface. And usually you're looking kind of a wet microburst situation, especially with the serial and progressive. All right, so we'll talk about this more on the next lecture, in lecture 6, with shear vectors. But this is a great kind of like precursor to that. When you're looking at shear vectors, now everyone looks at it a little bit differently, but I like to look at it between about 0 and 6 kilometers between the surface and about 500 millibars or so. But to keep this keep this simple for now, the more perpendicular the shear vectors are to the boundary. So if you have a squall line, the more perpendicular in general, even though if it becomes too perpendicular, it actually can cause the storms to split. But for now, let's keep this simple. The more perpendicular to the boundary it is, this will lead to propagation, all right? The squall line will move, it'll propagate, right? Whereas if it's parallel, if it's not perpendicular, if that 0 to 3, 0 to 6 flow is parallel, and again, I look at more 0 to 6. If it's parallel, then you're not going to get that same propagation, all right? Maybe a little confusing now, but when I show you with supercells and severe weather types, it'll make a lot more sense. But this will tie into that later on. All right, so here's an example with a higher cape, and you lead, especially if you have a nice cold pull balance, you get a stronger rear flow jet. Makes sense. If you have higher cape with a strong cold pull, even though it's still in balance, but they're at high, high cape, nice cold pull, that balance will really form a nice rear inflow jet. Where if it was weak and you just had a really slight unstable environment with a weak cold pull, you're not going to get as strong of a rear inflow jet. So basically with this, all I'm trying to show you is the more imbalanced and the higher that cape and the colder that cold pull is and the more imbalanced it is, the stronger it is, the faster that rear inflow jet will be. And in theory, with that, with evaporation, the faster those winds will be at the surface as well. It makes sense. If it's stronger and more imbalanced, then you should have a worse event. And here again, the wet microburst sounding. I showed you this in the previous lecture, but you got that dry air. Now remember, I told you I like to look in this area here, and you're starting to see 40, 50, 45, 50 knots of wind. So if I looked at this and I knew, this area was going to, with precipitation, was going to moisten and this air was going to come to the surface, I would expect at least 45, 50 knot winds in this case. Whereas if it was really weak winds here, the winds were not very high, then I wouldn't expect near as high winds at the surface. So that's something I like to do. I like to look at that dry pocket and then look over at the winds, and that gives me a good idea what the potential of the winds are at the surface. All right, we'll end with the climatology here. The pattern derechos occurrence is a distinct one. The greater incidents tend to follow the mean position of the jet stream, which makes sense. I mean, obviously, if the jet's cutting more to the south, then it'll affect us more here in Mississippi in the deep south. And if the jet is staying more to the north, then the worst of it would stay well north of us, right? So it depends on the time of the year, and now again, you got to be careful. Just because it's summertime doesn't mean you can't get a nice strong cold front through here. But in general, the seasons kind of dictate the formation of this jet stream, right? So here's just the overall climatology, right? Looking between 80 and 2001, you see it's all over the place. I mean, you get derechos here in Mississippi, Oklahoma, Minnesota, Ohio. It's all over the place. So you get derechos everywhere. But let's break it down. The more the cool season, more September to April, right? Which is typically with what? The serial derechos. What's going on? We get a lot more here in Mississippi. Well, why is that? Well, the troughs are digging in, but we still have enough instability to balance it. Where to the north, yeah, the troughs are digging in, but it's so cold and dry and there's no instability, it's going to be really difficult to get derechos in general, all right? Now, you got to be careful, because that doesn't mean you can't get them at this time of year. It's just more typically going to occur where, what do we have here? Gulf of Mexico, more instability, and it kind of goes in the winter severe weather season here in the deep south anyway. But what changes? We get more progressive derechos in May and August. They're more to the north. Well, why is that? The jet stream is shifting more to the north, and you still have decent instability, so this is where the derechos will kind of set up this time of year. Now, does that mean we can't get one this time of year? No, it doesn't. But again, in general, the seasons kind of dictate where these set up. So hopefully that makes sense. So again, this was just, a fairly short lecture, just kind of breaking down how derechos work, how you can look at them, and hopefully now when you look at radar, you can at least know where the apex is. You can see that rear inflow notch. You can know where the fastest winds are. You understand a little bit about bookend vortices. You understand between serial and progressive. So hopefully when you see these events evolve, you'll at least have a baseline where to start. And if you want to keep getting better at this, obviously practice, but Comet has some really good modules on this. And then, of course, Google's your friend. Always look things up, because the more you practice with it, the more you look. And even me, I learn new stuff all the time. So again, it goes back to practice, and the more you look at it, the better you'll get. All right, I'll be back here soon with Lecture 6.